After the preparations in the last videos, we're now ready to compute the regular functions on these distinguished open sets we defined. Let x be an affine variety and f a function on x, then the regular functions on d of f, the locus where f is non-zero, are all given as functions by these quotients g divided by f to the m, where g is any function on x and m is a natural number. So in other words, on d of f, the functions that are allowed are the quotients of some polynomial by some power of this f. In particular, if you specialize this to f equals 1, then we have d of 1, the locus where 1 is non-zero, is still equal to all of x. And so we see the regular function on all of x are just given by g divided by 1 to the m. So in other words, just by g, where g is an a of x. So this is just equal to a of x. In other words, the regular functions on all of x are exactly the polynomial functions. And then the second observation here is that on these distinguished open sets, it is true that a regular function is just globally the quotient of two polynomial functions. We have seen an example that if you choose the set U very carefully, in that example, then you can get a regular function which is not globally the quotient of two polynomials, but at least on these df's, this can never happen. And the proof has an easy part and a hard part. The easy part is this inclusion here. Well, if you have such a function, then first of all, it makes sense on df because, well, f to the m is non-zero, so you're allowed to divide by this. So this is a well-defined function on df, and it is a regular function because it's given by quotient of polynomials. And so certainly all of these things are contained in here. The hard part is the other direction. And so let's get started with this. So let's say phi is any regular function on df. So by definition, for each x, for each a inside df, you have an open neighborhood, UA, on which you can write phi as the quotient of GA divided by FA, where these are polynomial functions on this open, which have the property that on this open neighborhood, at least the f of A is non-zero. So until now, we have just kind of entered the definition of phi being a regular function. And basically, the first part of the proof is now just start with this data and start manipulating it a bit and making it simpler and simpler. Like we will have a series of steps, which I'll kind of mark in green, where we observe that we can make additional assumptions on these UAs and FA, GA, and so on. So we start simplifying our situation, and in the end, our goal is to reach this global form phi is equal to g divided by f to the m. Okay, so let's slowly get started. First of all, this UA is a priori just any open subset in X containing A, which has this property here. But we have seen that the distinguished opens form a basis of the Zariski topology. So in other words, around this point, we do find some basic open, which we call D of HA, which is contained in the UA. And in this form here, we're always allowed to shrink our neighborhoods. So in other words, we can shrink the UA and just assume that UA is given by this distinguished open subset DH of A. So that's the first step. From now on, we assume UA is equal to DHA. The second step, now that we have this, is that we can change this representation of phi slightly. Phi is given by GA divided by FA. we can multiply by HA, both in the numerator and denominator. This is allowed because HA is still non-zero on our UA. So we haven't changed this condition that the denominator shouldn't vanish on our open set. And what this has given us is that now after multiplying this here, it's true that both the numerator and the denominator vanish outside of this open set D of HA. And so by replacing GA by this product and FA by this product, you can just assume that GA and FA vanish outside of DHA. Okay? That's the second assumption. We replace everything. And so from now on, we can also assume this here about our data. And then the final kind of replacement that we want to do is now if we look at what does FA do at different points X, like is it 0 or non-zero, then we see, well, if X is in D of HA, if it is in the open set, then this value here is still non-zero because we had assumed FA is non-zero and the HA is also non-zero on DHA, so the product is still non-zero. So here, if X is in DHA, FA doesn't vanish. On the other hand, by this manipulation here, when X is in the complement of DHA, then by definition, or by the assumption which we added here, it does vanish. And so staring at this observation here, we see the vanishing, or somehow the complement of the vanishing set of FA is exactly the same thing as the complement of the vanishing set of HA, right? Because FA is 0 if and only if HA is 0, just from this equality here. So they vanish on the same loci. So in other words, the distinguished open sets for these two things are the same. And then, kind of to simplify our lives, we can just take as HA to be the FA. Because, I mean, if you replace HA by FA, this doesn't change this set, this distinguished set. So in other words, we can kind of get rid of the HA, and then we just have two data points left, FA and GA. Okay, so this was a series of simplifications, and what this has given us, I just want to summarize again. Namely, the summary is, for this function phi we look at, it is true that for any A in DF, we have phi is given by GA divided by FA on this open neighborhood of A, so on all of DFA. And we have one additional assumption. This came from this kind of second step here, namely that the function GA vanishes outside of DFA. That we have. And this is the kind of crucial input in the second part of the proof now. So until now, what we have done is we just manipulated how this function phi is represented around each point A. But now we want to use that, of course, all of these local representations give the same function phi. And now we want to make a connection between these various different representations. And the big claim here is that for any two different points in DF, well, we have these functions FA, GA, FB, GB, and our claim is that they satisfy this equality here in A of X, that GA times FB is equal to GB times FA. Okay, how do we see this? We will check this equality of functions on X on some decomposition of X. We will check it kind of separately for X in, first of all, in this intersection, DFA intersected DFB. the locus where both of these things are non-zero. So in other words, x minus the vanishing loci here. So this is the first locus where we check the equality. And then we check it also on here and on here. And then these three sets cover all of x. And so once we check this equality on all of them, we know it inside A of x. Okay, and this one here is in a certain sense the most obvious one or the easiest one, namely if x is in DFA intersected DFB, well, this is exactly the locus where phi of x is is given by both these representations. So phi of x on the one hand is given by GA divided by FA, on the other hand given by GB divided by FB. Okay, and then if you take this equality of denominators and you this equality of fractions and you multiply by the denominators, you just get this equality here, and this is exactly what you want to show. So on there, the equality here is just literally the equality which guarantees that both of these representations define the same function. And then on the other point, so if x, for example, is in Vx of Fa, then, I mean, by definition, Fa of x is 0, but also by this condition here, Ga on V of Fa is also 0. So this thing and this thing vanish. And then you see somehow Fa is on the right-hand side of the equality. This vanishes. And Ga is on the left-hand side, so this vanishes. So the equality is satisfied because it just says 0 equals 0. And then by the symmetric argument, so this was in Vx of Fa, and the symmetric argument also gives exactly the same thing for Vx of Fb. Okay, so we have checked it on all three elements of this cover of X, and so this thing is true. And this relates the representation of phi on different parts of this open cover. And now we're in good shape to finish the proof, because now we want to get to one global representation of phi. And this will be done using this kind of technical lemma that we saw in the last video. So we have that D of f is now covered by all of these DFA on which we have the representations. And then this lemma from last time, which was called the partition of unity, this tells us that some power of f is then given as a finite combination of the Fa times Ra, where Ra are polynomial functions on X. So that's the point where we use the partition of unity lemma. And from that representation, we just make the definition G is equal to the same combination of Ra times Ga's. So the Ga's appeared before. A priori, this just comes out of nowhere. Well, it is a well-defined thing. It's just a well-defined finite combination of these functions. And our claim is this is exactly the right thing to take, namely that phi is given by G divided by f to the m on df. Certainly, I mean, wherever this came from, it would finish our proof because this is exactly what the proposition says. And what we now just do is we check this equality here at any point B in df. And then we're done. So let's say B is some point in df, and then by this kind of representation, so by this thing here, we know phi is given by GB divided by FB at the point B at least, and in a small neighborhood. And then we just want to check that this here is the same thing as this at this point. And again, we check this after clearing the denominators. So we start by saying G times FB on this side here. We want to start manipulating this. And then we just plug in the definition of G. We get the sum over RA times GA, and still this FB. And now here we see we have this term GA times FB. And then in this blue box, we saw GA times FB is equal to GB times FA. So we can kind of switch the indices here. And now you see this is the sum over A. So we can draw the GB outside. And then we're just left with the sum of RA times FA. But this was, by definition, this was exactly what we wanted to define the F to the M. So we had drawn this outside, and then we have GB times F to the M. And this equality here, this is equal to this. This is exactly, after unclearing the denominators, we see that GB divided by FB is equal to G divided by F to the M. And this was the representation which gave us phi of B. And so phi of B is given by this quotient here. And so we checked the equality. Okay. So I admit this part, like this, fell a bit out of the sky, but essentially it was just exactly the right formula to plug in to have this representation, because we could use this trick at this point. Okay, so this finishes the proof. So indeed, all of these functions are given by these quotients. And I just want to have one more remark, because in the proof, at one crucial step, I claim we used that K is algebraically closed. And the point where we use this is exactly this lemma on the partition of unity. Like this allowed us to write this thing here down. And because, I mean, somehow you can always recognize where K algebraically closed is used, because this is where the Nullstellensatz comes in. And the Nullstellensatz with this kind of F is in a radical, this exactly explains where this power here came from. Okay? Just as a side remark. But somehow we used that K is algebraically closed. And it turns out that the statement of the proposition is just false if for a moment we drop this assumption. In particular, I mean, one part of the statement was if we set F to be 1, then we saw that the functions on X, the regular functions on X, are exactly the polynomial functions. And well, we can see a counterexample to this for a non-algebraically closed field. Namely, take K to be the real numbers. So X is just, and then X is the affine line of dimension 1 over the real numbers. Then on there, you can write down a nice quotient of two polynomials, namely 1 divided by x squared plus 1. And this is a function defined everywhere because the denominator is never 0, because x squared is non-negative, so x squared plus 1 is always positive. And this is a regular function by the definitions that we had before, but it is not globally given by a polynomial, because, for example, its value goes to 0, whereas the only polynomial whose value goes to 0 at infinity is the 0 polynomial. So we see that it was really crucial that K is algebraically closed, and this allowed us to have this lemma on the partition of unity. Okay, so this was, again, the proof that regular functions on D of F are just given by quotients by F to some power. And this we can use in the following to compute these functions also on more complicated sets.